I'm going to talk, I'm going to give, I'm Sam. I'm going to give an introduction to the Crimson project and then talk about some of the recent development work that we have been doing. So the main driver of the Crimson project is that storage technologies are driving towards higher IOP density and lower latencies. But CPU throughput isn't really improving on the same trajectory. We do see an increase in core count, and but we see an increase in core count, but not an increase in per core throughput in quite the same way. So we need, with a hard disk, you might get 20 million cycles per I/O, but with NVMe devices, it's single-digit thousands. Thus, we need to drive down the CPU per IOP cost in order to be able to cost-effectively exploit these newer, faster devices. However, Ceph was created mostly with hard disks in mind, so the software architecture tends to be relatively heavy on CPU usage, particularly with respect to scheduling. So given this kind of IOP density and core count, we really want a highly parallel architecture with low CPU overhead per IOP. So we're looking for a way to adapt the OSD in particular to hit this goal. Here's a graphical representation of CPU usage in Classic-OSD. I borrowed from Kifu and Radek's presentation at Cephalicon Barcelona many years ago now. We can see several of the OSD's thread pools represented here. The BlueStore FN Anon anonymous finisher thread, the messenger thread, and the OSD thread pool, TP-OSD TP. So if we zoom in on the request commit callback, because the callback needs to reach into PG structures, which are also used in the OSD op thread pool, we spend quite a bit of time acquiring locks to permit access to these resources. If we zoom in further to the nested, or to the callback, we see even more locking over the state responsible for watch notify. You can also see that we spend quite a bit of time in the kernel TCP IP stack, sending and receiving messages. So there's quite a bit of CPU overhead inherent in the classic OSD threading architecture alone, even before we get to the implementation of any of the IOs. The Crimson project is meant to solve this. At its core, the project has two major goals: minimize CPU overhead per IO, including cross-core communication, copies, and context switches, and secondly, to exploit emerging storage technologies like fast NVMe. So to that end, Crimson is a rewrite of the OSD daemon intended to address these goals. It's important to note that it's IOPS per core that's the important metric here, rather than raw IOPS. Classic OSD can drive a substantial amount of throughput. It's just that it requires a lot of cores. So we want to reduce that property. And what we saw before is that the core reason for this is that the context switching inherent in the threading model used for classic OSD contributes a lot of latency and overhead. Crimson avoids this problem by pre-allocating a single thread per core and partitioning data, structures, and work among cores as much as possible so that accesses are core local, making locks unnecessary. So broadly speaking, there are three main components of the OSD IO pipeline. There's the messenger, the PG state blob of in-memory state used for operation ordering, recovery, etc., and BlueStore, or whatever ObjectStore implementation, responsible for actual IO and transaction atomicity. So for small unreplicated write, the client message is read off the wire by the messenger thread, which places the message in the op queue. The OSD op thread pool then picks up the message, creates a transaction, which it queues for BlueStore. BlueStore's KV sync thread then picks up the transaction along with anything else in the queue, synchronously waits for RocksDB to commit the transaction, and then places the completion callback in the finisher queue. The finisher thread picks up the completion callback and queues the reply for a messenger thread to send. Each of these thread handoffs requires coordination over the contents of a queue, and with PG state in particular, more than one thread may need to access the PG data requiring mutexes. By contrast, in Crimson, the goal is to localize all of the parts of this pipeline into each thread. So assuming the message arrived on the right thread, the messenger, the PG, the object store, and the reply back to the messenger could all be handled by the same thread. We're using SeaStore, a user space scheduling library, to do this, and rather than passing around callbacks, SeaStore uses these future objects, which allow us to chain asynchronous handlers onto I/O results. And SeaStore handles switching among tasks as their I/Os become available. So the other big component of the Crimson project is SeaStore. As I mentioned before, the other goal is that we want to be able to exploit new emerging storage technologies like NVMe and zone namespace storage. SeaStore is how we will do that. SeaStore is a new object store implementation designed specifically for Crimson's threading callback model. It avoids CPU-heavy metadata designs like RocksDB, and it's intended to exploit emerging technologies like ZNS and NVMe. So what is ZNS? It's a new NVMe specification intended to address challenges with conventional FTL-based flash designs. Conventional flash devices use garbage collection to empty erasure blocks for reuse. This tends to cause fairly high write amplification, which is to say each write to the device tends to result to multiple devices within the device. And this is bad for QLC flash because QLC flash has poor write endurance. Each cell can only be written a comparatively small number of times. And background garbage collection tends to impact tail latencies, in that garbage collection within the device can compete with client I/O for device resources, resulting in periodic latency spikes. ZNS addresses this problem by creating a different interface, where the drive is divided into zones, which can only be opened, written sequentially, closed, and then released. We're interested in addressing these devices both because we think they'll be specifically useful for QLC, but also because this write pattern tends to be good for conventional SSDs as well, since it reduces the amount of traffic the garbage collector needs to handle. So I mentioned that SeaStore is an object store interface. So like BlueStore and FileStore before it, object store interfaces or implementations are transactional, composed of a flat object namespace. Object names may be large, since Rados objects map directly onto object store objects. Each object also contains a key to value mapping, which we use for a few things like ceph-osd directories and Rados GW bucket indices, as well as a data payload, which you're probably more familiar with, as, for instance, the 4 megabytes of data associated with each RBD block. It also supports copy on write object clones, which is how we support Rados level snapshots, which translate up into RBD and ceph-osd snapshots. And it supports ordered listing of both the OMAP and object namespaces, which is important for just basic functionality of bucket indices and directories. And for the object namespace, it's important to how the OSD does object recovery, backfill specifically. So SeaStore's logical structure looks something like this. There are 2 basic sides to the house. On the left side here, we have an onode by object tree, the onode tree, which points to onodes, and each onode contains metadata pointing at an OMAP tree and a set of extents, which are contiguous blocks of LBAs. Everything on the left side of the tree here is addressed by logical address rather than by physical location on disk. The right side maps those logical addresses to physical addresses on disk. So why do we use an LBA indirection? There are a few reasons. One is that is basically write amplification. When we need to, let's say we have references A referencing B referencing C, and we need to garbage collect node C, or just to move it to a new ZNS zone so that we can reuse the zone. We would first need to find all incoming references, which could be expensive without a secondary structure. And then we need to write out a transaction updating and dirtying those references, as well as writing out a new block C prime. Using direct references means that we would need to maintain some way of finding the parent references. In ButterFS, I'm forgetting the name of the structure, but there's a structure for it. And we pay the cost of updating the relatively low fan-out ONode and OMAP trees, since the keys in those trees are relatively large. By contrast, using an LBA indirection does require extra reads in the lookup path, but they're cacheable, and it potentially decreases read and write amplification during garbage collection, or indeed during tiering operations where we're moving blocks between tiers. It also makes ref counting and subtree sharing for copy on write clones easier, and it allows us to do sparse mapping for object data extents. Since within an object data payload, we can simply declare a portion of the LBA space to belong to that object. So the on-disk layout when we're writing out journal segments looks something like this. Each journal transaction contains a header, some number of deltas, here represented by these blue blocks, and then some number of logical and physical blocks represented here by the magenta color. So the left side here is the state prior to the transaction, and the right side here is the state after the transaction. D prime and E prime are the mutated versions of those two blocks, which and B and A are new blocks being added to the tree. If we're using ZNS append, we don't actually know the final location of A and B, so this transaction record format allows the E prime to A and A to B references to be record local. So they're represented as offsets within the record, so that it'll be correct regardless of where the record ends up. And then during replay, since we have the record address, we can resolve those relative addresses. So the overall architecture looks something like this. Up at the top, there's a SeaStore layer responsible for the ObjectStore interface itself. Below that are the portions in blue responsible for operations on logical data. The ONode manager is the tree responsible for dealing with ONodes. The OMAP manager deals with the OMAP tree. Object data handler deals with the object context, etc., or contents, etc. The layer in the middle, the transaction manager, handles all of these logical block mutations uniformly as operations on a logical address space. And then the portion below that is responsible for translating those into operations on physical nodes, with the LBA manager being responsible for the LBA tree I mentioned before. The advantage of this architecture is that the things above the transaction manager do not need to be aware of garbage collection or tiering. The transaction manager and the stuff below it can transparently handle moving blocks around, and the stuff above doesn't need to know about it. So, the main purpose of this talk, I think, is to go over some of the recent work that's gone into Crimson and Seastore. Because Crimson is effectively a rewrite of the OSD, the story over as it matures will be a story of adding features that already exist in Classic-OSD. So the main goal for Reef is to have an initial kind of experimental release that people can try out for RBD workloads on replicated pools. So to that end, a lot of work has been done stabilizing the BlueStore RBD Rados tests. There's a Teuthology suite that we've now split into Crimson Rados and Crimson Rados Experimental. The Crimson Rados suite now generally passes after a great deal of work by Chun Mei and others, and will soon be used to gate PR merges, which will be an important step to Crimson becoming a real usable implementation. The other top line sort of thing for Crimson this year has been Multicore. Because our initial functionality or our initial goal for Crimson was to drive down per core, or was to improve per core throughput, we initially focused on a single core implementation, and we didn't worry about actually partitioning the data structures. We were pretty satisfied with those results. So this year, a lot of work went into splitting the PG state among multiple cores and introducing the internal architecture required to route messages between cores. The next step here will be further improvements to this and adding multi-core support to the messenger natively. Another thing that's seen a lot of work this year has been snapshot support. The basic I/O path components are implemented, and trimming and recovery components are in progress, and they may be complete for Reef. Another thing that was important recently is if Crimson is going to start seeing wider testing, we needed to add some user guardrails to prevent people from accidentally creating Crimson-OSDs and that kind of thing. So we've added an experimental feature flag. So if you're actually trying to deploy it, there will be updates to the documentation that reflect this. But you need to set an experimental feature flag, and then on the whole cluster, you need to set a set allow Crimson OSD map flag that Crimson OSDs will want to see in order to boot. The other piece is that pools will need to be created as Crimson pools. And the monitor has some code to gate some features that aren't supported in Crimson yet. For instance, you can't create Crimson erasure-coded pools, and you can't change the number of PGs on Crimson pools or set them as tiers. The intention ultimately will be to allow mixed clusters between Crimson and Classic, especially during the transitional period when Crimson doesn't support everything. So that you might be able to create a Crimson pool specifically for RBD and another pool for an erasure-coded RGW pool, that kind of thing. So the current status that we're hoping to get ready for Reef is RBD workloads and replicated pools will work for on BlueStore. It'll include BlueStore and SeaStore backends, as well as the Cyan store in memory backend, but the SeaStore one will be even more experimental than the BlueStore one. Deployment via ceph-ADM should work relatively smoothly, and there's some documentation for that. And for developers, you can, of course, use vstart to, with the -- Crimson flag. And there's a stable Crimson Rados technology suite, which by Reef will be used to gate new PRs. Tests that do not yet reliably pass, including the SeaStore ones, are in a Crimson Rados experimental suite. So the next steps for Crimson are going to be continuing to expand test coverage. Many of the thrashing patterns, for instance, are not yet stable. We want a scrub implementation because without that, we won't have particularly good confidence in correctness. Some work has already gone into refactoring the scrub use within Crimson, and that's mostly complete. So the remaining work is basically adapting that work into Crimson itself, much like we did with peering. The other thing for Multicore, the next step will be supporting multiple reactors and generally doing performance testing and improvements based on profiling results. And the other big theme of the S release will be performance improvements now that Multicore support is in place. So the Yingjin, I think, is going to talk a bit more about SeaStore, so I won't go over this in too much detail. But the major theme for SeaStore will be, or has been, stability. A ton of SeaStore tests have been added to Tethology, now in the Crimson Rados experimental suite, and it can reliably complete the Rados API unit tests. A bunch of work. a lot of work has gone into SeaStore's tiering implementation. A major goal is to support heterogeneous configurations combining expensive but small, expensive, fast NVMe devices with slower, bigger, cheaper QLC devices. So you get sort of the best of both worlds. So to that end, recent work includes a random block manager has been introduced to handle fast NVMe devices without needing to use garbage collection so much. And direct tiering support is in progress with a lot of the architectural groundwork already merged. So S release will see a lot more of that usable. There have been a ton of improvements to for performance. The garbage collector has been replaced with a generational implementation that does a better job of grouping extents by age. And there have been a lot of improvements to the way the LBA tree works to reduce the number of reads we actually need to do and improve the CPU efficiency of traversing the tree in memory. So next steps are even more stability. We need to stabilize the SeaStore tests in Crimson Rados experimental so that we can get them moved to Crimson Rados. We want to add multi-core reactor support to SeaStore. There's already PR for some initial version of that, but I expect there will be quite a bit more work that needs to be done for S release. We'll want the next step for tiering would be to get an actually usable initial implementation with testing. SeaStore also does not support snapshots yet, so that's an important piece of outstanding work. And as with Crimson as a whole, an important theme of the next year will be further performance improvements. So that's all I've got. Does anyone have any questions?
So if someone wanted to try playing around with Crimson at this point, what would they do, Sam?
If you're a developer, you'll want to use the vstart instructions or --crimson flag. There is some documentation in the docdev OSD or Crimson documentation page on how to deploy it with ceph-ADM. And that documentation should improve just as soon as I can merge some PRs that are outstanding right now due to the stoppage in the lab. So either of those options is doable. Will Crimson support EC in the future in some point in time? Probably. I mean, well, okay, so long-term, the goal is to flat out replace ceph-OSD. So in that sense, yes. It may not be an immediate priority for two reasons. One, erasure coding workloads aren't usually all that performance sensitive, so it's not as good a way to prove out Crimson. And the implementation is largely will benefit from all of the other work being done. So, for instance, the implementation of Scrub will be using abstraction barriers that will just natively or that will naturally support erasure coding when we get around to it. So, yes, it will eventually support it. Exactly when will depend on when someone wants to work on it, basically. I'm not willing to commit to a when Crimson might be ready for production use, but the intention is in S release for very knowledgeable users who have done a thorough job of evaluating it with respect to their use case. Those users may be able to use replicated pools with RBD in a quasi-production setting. There will likely still be rough edges, so it'll likely be several releases from them when that becomes more ergonomic, but that's the intention. So not release, or not Reef, but maybe yes, James. No promises though.
All right, well, oh, question just popped in.
I
Any,
don't have any offhand, Stefan. We'll probably be, now that the multi-core work is done, we'll probably be generating numbers again in the coming months. So with the reef release, that may be something I try to publish.
in case you're watching the recording, that question was any performance numbers you can share compared to current Quincy. All right, Sam, thank you for the update.
Yep,
Looking
thanks.
forward to that reef release to try it out.